this is your domain, and let's do this is your plane. Okay, now we fix a point on the domain. Now you get the corresponding point. So this is z equals x, so now we want to find the tangent plane to the surface at this point. Okay, so this point is what? This point is a b f of a comma b. That's the point, three-dimensional point. Now you want to find equation of the tangent plane at this point. Remember, we're doing the two-dimensional version. In one dimension is the tangent line, and here we're doing tangent plane. So to do tangent plane, we know the point. Now you just need to know that tangent normal vector. So the tangent plane would look like something like this, right? So this is the tangent plane. Now to get the tangent plane, you will need to know the normal vector. So this normal vector. How to get the normal vector? So to get normal vector, first look at if you look at this line, this is a tangent vector, right? So that means this is corresponding to this. So that means you fix y value and x value changes, right? So then this is the change of height of the surface when x is changing at a, y is fixed. And we already know, so these vectors be what? If the direction will be, if x changes 1, y doesn't change, and z is gonna change fx at AB. So I'm writing this as a t vector along x. Okay. Now if you do along y, so did I did it wrong. Here y is changing, x is fixed. I think I need to erase this. So y is fixed. I mean x is fixed here. X is fixed. Y is changing. So that means what? X is fixed. If y changes 1 unit, what is z is gonna change? The rate of change given by the partial derivative. That's this. And that vector is I'm writing as dy. Now let's do when y is fixed. Now when then x is changing, then with change of x, now we want to see how z is changing. If you look at that, it will be like this. Right? That is the tangent line. So here, what is the vector going to be? Y is fixed. If x changes 1 unit, z will change that partial derivative of f with respect to y at AB. That's the meaning of partial derivative, right? The rate of change at AB with respect to y. Now think about what we got. we got two tangent vectors. That means these two tangent vectors are on the plane. So if you want to get normal vector, so you take cross product of these tangent vectors. So you can write as a ty cross tx. You can do other way too, it doesn't matter. I'm writing ty because, you know, so there's write ty. So now you do cross product formula. Ty would be what? 0, 1, fy at AB, and px is 1, 0, fx at AB. So if you do that, I something j something k. So if you look at I, get it out faster first column, it will be 1 times f of x.
Should the orange vector be f of x? Because it looks like it's f of y that you wrote it down as.
Yeah, I wrote it wrong. That should be it.
Thank you.
Because I'm writing as a tx. Thank you. Now if you do j, get rid of the second column and first row. So this times this minus this times this. So 0 minus f of y. Now first row and third column gets of this 0 times 0 minus 1 times 1. So to write as a vector, it is just f of x partial derivative with respect to x at AB, and partial derivative with respect to y at AB, and this is negative 1. So that's the normal vector to the tangent plane. So the point is this point AB f of y, and this is the normal vector. So you know how to do that, right? So n dot r is n dot the point, right? X naught, y naught, z naught. In this case, a b f of ab. You can say f of ab is c if you want to. If this point is abc, so just I can rewrite this as c. This is the point, and the tangent vector is here, so I'm just writing without the ab. Um, then actually I can subtract this. It's probably better to write this. Probably I can save some time. I'm rewriting this. So n dot r minus abc is going to be 0. So then if you do that, it would be x minus a, y minus b, z minus c equals 0. Not that. If you do that, f of x times x minus a, f of y times y minus b, plus negative 1 times z minus c equals 0. Okay? So if you write it down, write it here. You write z on the right hand side. If you do that, it would be z minus c because f of x ab times x minus a, f of y at ab minus y minus b. So this is the equation of the tangent. Does that make sense? Why this is the equation of the tangent line? Using the partial derivatives, we got two tangent vectors. And the cross product is going to be the normal vector to the tangent line. Okay, let's do a quick problem. So, using this. So find equation of the tangent line to the surface z equals 2x minus squared plus 2y plus 3 squared plus 7 at the point 2, negative 2, 12. You can check 2, negative 2, 12 will satisfy this equation. So this is indeed a point on the surface. Now you have to just plug it, right? So you need to, if this is z, so you need to um, get zx, which is fx. So what is zx? You take partial derivative with respect to x. It is 6 x minus 1 plus 4 y plus 3 plus 0, right? You're treating, okay, sorry. See this mistake? It can happen. If you take partial derivative with respect to x, y is constant, right? So this should be 0. Clear? And what is zy? You take x as a constant, so this would be 0. And then it will be 4 y plus 3. I'm using chain rule, right? Something squared means 2 times that thing times the derivative of y, which is 1. Now you're plugging at 2, negative 2. So zx at 2, negative 2 is going to be what? X is 2, so 2 minus 1 is 6. And zy at 2, negative 2, you're plugging y equals negative 2 is 4. So what is the equation of the tangent line? We are plugging this z minus c in this case 12. Then zx, which is 6. Then x minus a, which is 2. Then fy, which is 4. And y minus b is negative 2. Negative or negative would be positive. So this is the tangent line. Any question how you get the tangent line to a surface at a point? Sorry, tangent plane, not line. Good. Questions? Okay, so let's move on. So now linear approximation. So in one variable, so remember the picture, in one variable, so if you know the height at this point, A, and you want to know height at a nearby point, a nearby point height would be this. But if you want to approximate that height, what do? You draw a tangent line. And the height of the tangent line is the approximation of the height of the actual curve. Okay. So similarly, do for three dimension, I mean two variable functions. If you have z equals f of x, y, and if you zoom the surface near the point A, B, C, The surface looks like what? If you zoom really closely, it would look like any surface, continuous surface would look like a plane, right? Similarly, if you zoom near this point, any curve would look like a line. The surface looks like the tangent plane. That means if you look at the height of the tangent plane, that is approximately the height of the actual surface. So that's the way you do the linearization. So the linearization of f at a point AB is just the equation of the tangent plane. Do you see this is just the equation of the tangent plane? Instead of writing z, I'm writing a two variable function. Okay. And that means if you want to approximate the linear or tangent plane approximation of f at AB is, or near AB is, if you take a nearby point, xy, the nearby point is just gonna be the linearization. That means this thing. Okay. If you take xy, is then here this means as xy close to the point AB. Then fxy is approximately L of x. So let me do a quick problem. Find the linear approximation of the function at 1, 1 and use it to approximate the function at a nearby point. You see, at 1, 1, you can find it. If you want to find a nearby height, then we are going to use the linear approximation to do that. So basically, linear approximation means not height of the surface, but the height of the linear tangent plane. So first tangent linear approximation would be what? Lxy is f of AB plus f of AB means you're plugging 1, 1. So if you plug 1, 1, so I'm just writing 1, 1 instead. So if you plug 1, 1, this is cosine pi, right? Cosine pi is negative 1. So this is going to be 2. So what would be fx? So taking derivative with respect to x, treating y as a constant, right? The y cosine pi y. What would be fy? We're treating x as a constant, right? So first derivative of y which is 1 cosine pi y. And then xy times derivative of cosine pi y, which is negative sine pi y times pi. So I use product rule plus chain chain rule. Is it clear why fx fy like this? So if you plug 1 1, cosine pi is negative 1, so it will be positive 1. Then x minus 1. If you plug 1 1 here, what do you get? This is positive 1 and this is 0. Sine pi is 0. So this is just positive 1. So this is the linearization. In other words, you just find the equation of the tangent plane. You replace this Lxy by z, that's the equation of the tangent plane at 1 1. Okay? So if you want to find f 1.02 and 0.97, this is approximately what? This is the height of the surface. You can approximate that by height of the tangent plane. This is approximation, by the way. It's not equality. Now this equals 2 plus 1 times 1 minus 0, 2 minus 1, 1 times 0.97 minus 1. This will be what? 0.2. And this is 0.03. 0.02, right? It will be what? 1.99, which kind of makes sense. At 1 1, the height of the surface is 2. At 1.02 or 0.97, if you change a little bit, the height also changes. Height of the surface changes. But what we found, this is the, remember, this is not the height of the, this is height of the surface. Which is approximated by height of the tangent. Any questions? Luke, are you saying something?
No, I'm just singing a song in my head. My bad.
Song about calculus?
Yeah, there's a few songs that came out about calculus a few weeks ago.
Are you sure?
No.
All right. Any question on this? So this is easy part. Now I'm going to talk about something really difficult, but I'm not going to ask you any difficult question on that. The differentiability of a function in one variable is very easy concept, but in two variable is much more difficult concept. So before I do that, let's talk about differential. Okay. In one variable, if y is a function of x, y is a function of x, and you're taking a derivative at a. Now, if you go a little bit beyond a, this is a plus delta x. Then obviously the height will change. The height would be here, right? So then is this difference is delta y, right? For delta x difference, you get delta y, right? But what is dy? Delta y is the increment in height. But what is dy? So dy is if you draw a tangent line at this point, dy is the change of height in the tangent plane. So dy is this. So that's the differential. So delta y is change of height of the curve y equals f of x. What is dy? Dy is the change of height of the tangent plane, tangent line. So this is the differential. This is differential. And this is increment in y. Okay? Clear? So one variable, what differential and increment y, they are not the same thing. But when they are really close, delta x is close, they are approximately equal. Now this is one variable. What do you do in two variables? Two variable graph is a surface, right? So suppose if the point is, let's say I'm taking AB 0, this is the point, and the corresponding surface looks like, let's see, looks like this. So this is z equals x. Okay. Now if you take a nearby point, like this is not nearby, but let's say take this point. Okay. And so this is the horizontal plane. So this is z equals f of a, horizontal plane. Okay. So now the tangent line would be what? Tangent line look like, this is the tangent line. Tangent plane. Okay. So maybe I take a point here. So if you take a point here, nearby point, look at the height difference. So the surface will actually go a little bit farther. So maybe I'll draw it. If you look at the point, um, the height difference. So if you take a point probably here, and if you go to the surface, so from here to here, that's the change of the height of the surface, right? If you go from this point to this point. So this is your increment in z, okay? That's increment of z. What is differential? Differential is, I have to use a different color. So the differential is the change of height in the tangent plane. That's dz. So in one variable, this is what you have. dy equals a prime x dx. That's one variable formula. I'll give you the geometry. For two variable, what would be dz? Differential dz would be similar, but now you need to do partial derivative. Fx times um, dx and fy. Look at the similarity. In one variable, you just have derivative, right? But now in two variable, you need to take partial derivative. You just take similar. So what is dz again? This is the change of height of the tangent plane. Is it clear what's happening? Questions? So if you remember what we did before for the tangent plane. So this is at AB, it would be the one part, right? So fx, f of AB, then the rest part will look similar to this. So this is just basically dz. Approximately, because change is actually delta z increment. This is approximate. Okay, let's do a concrete problem. So suppose you have is a negative xy cosine y, and you're considering the point pi 0. So find delta z and dz when xy is changing from the given point pi 0 to a nearby point 0.1. Now pi is 3.1 for something, right? And this is a nearby point. So what is delta z? Delta z is just the difference between the height, right? So delta z would be what? So delta z is just so pi 0 minus f of 3.3. That means e to the 0 cosine phi or cosine 0, sorry, minus e to the negative 3 times 0.1 cosine 0.1. Cosine 0 is 1. So whatever that number is. That is the change in height of the surface of this graph. Now what is the differential? The differential, remember the formula, is f of x at the point pi 0 times dx, and then f of y at pi 0 times dy. But for small scale, delta x is dy, right? So dx is delta x. So what is delta x? Dx is delta x is change, right? Change in x. So it will be 3 minus pi. Oh, sorry, I have to do the other way. This is minus, this is plus. Sorry. This is the final value, this is the initial value. I realize from here. Now what is dy? dy is delta y, increment is y, which is 0.1 minus 0, which is 0.2. Now I have to take partial derivative also. Now you should be expert in taking partial derivative. You're treating y as a constant, right? So write cosine y, that's a constant. Derivative of e to the negative xy is e to the negative xy. By chain rule, now you take del x of negative xy, which is negative y. Clear? Now take fy. Similarly, we take, now this is a product rule. And it's getting complicated. Why did I choose this? The product rule, right? Derivative of the first, which is e to the negative xy, and derivative of negative xy would be negative x times cosine y plus e to the negative xy times derivative of cosine y, which is negative sine y. It would be, we take it to the negative xy as a common factor, or negative xy as a common factor, then it would be x cosine y plus sine y. Now we are plugging this at 0, right? If you plug at 0, pi 0, x is pi and y is 0. So cosine y is 0, that means this is going to be 0, right? And dx is 3 minus pi. And then you are plugging pi 0 here. So this is sine 0 is 0, cosine 0 is 1, x is pi, right? This is negative pi. This is 0.1. have. So any question on this? Okay, so the last one is differentiability. That's gonna be a little difficult, but I'll just give you a theorem that will make your life easy. So differentiability. This is a difficult concept. So for one variable, so for one variable, let me remind you what one variable differentiability looks like. Delta y at a, if you change the x value a little bit, then this is the increment in y. So we called f is differentiable at a if delta y, which can be rewritten as f prime a times delta x plus epsilon times delta x when epsilon approaches 0 as delta x approaches 0. This is the differentiability in a different form. So I'm not explaining details what that means. But let me explain in two variable, similar idea. In two variable, um, if g is a two variable function xy and f is differentiable at the point AB, if this is just if delta z is fx delta x fy delta y plus epsilon times delta x plus epsilon 2 times delta y. This is true when epsilon and epsilon 2 both approaches 0 as delta x, delta y both approaches 0. So this is a formal definition of differential two variables. So you really don't have to check using the definition because we have a theorem that is really helpful. So let me give you the theorem. The theorem says this is the theorem. If the partial derivatives exist near the point AB and continuous at AB, then f is differentiable at AB. So basically saying that if the partial derivatives are continuous, then the function is differentiable. Okay. So let me give you an example where if it is not differentiable, then things can get really bad. Linear approximation can be really bad. So, or maybe just let me give you an example quickly, because I have 2 minutes. We can continue this next time too. I mean, it's almost done. So if you have a quick problem, for example, if you have f of xy is x equals xy, and this is differentiable at 1, 0. So you need to take partial derivatives, right? If you take fx, partial derivative would be 1. If you take with respect to y, so look at these two functions. They are both continuous. Continuous at 1, 0. So f is differentiable at 1, 0. Okay. And let me just quickly show you where it does not work. And when it does not work, linear approximation fails badly. So here's an example. So you can see that if they both exist, also fx and fy are continuous, are not continuous, sorry. Exist but not continuous. And then that means it's not differentiable. It is not differentiable at 0, 0. Then linear approximation fails badly. As an example, if you do at 0, 0, this is 1/2 when xy approaches 0, 0 along y equals x, right? This is always 1/2. But if you do linear approximation, fxy is approximately 0 by linear approximation. But in real life, this is 1/2. So this is really fails badly because it's not differentiable. Okay, so look at the problems that I already posted. It's similar. The problems is similar to what I discussed. You can work on it. I can present tomorrow, and then I will start the section. The next section is gradient vector. That's the next section. So gradient and directional vector. So read about this before coming to class tomorrow. All right, guys. I'll see you tomorrow.
Excuse me.
Yes, go ahead.
When is the second test?